dramatic RL fine-tuning using SingleStoreDB, and we have a very special guest with us today. Aman, thank you so much for joining us. He is working at Apple, and he's one of the most fine leaders that they have at GenAI, and he has been associated very closely with the Stanford University as a fellow, and he has worked at great companies with rich experience at Amazon, Alexa, Nvidia, and obviously, you can check out his website. It's available on the slide right here. I'll be providing the links to everything in the chat. So stay tuned for that. As for me, I'll be your host and your moderator for the webinar today. So, and my name is Yukti. Keep an eye out at the chat button. I'll be adding links to everything in the chat. And for today, Single Store is also giving out $600 worth of free credits. So stay tuned for that as well. I'll be providing the link to that too. So just after, I'm done. And yeah, Aman, can you please go to the next slide?
Yes, yeah.
Thank you. So currently you are all in a listen only mode. Your microphones are muted. You might notice a small Q&A button which is present at the bottom of your console. So you can ask any questions that you might have. That is something that we use to interact with people. And towards the end of the session, we will also have a Q&A session. So that would be around 10 minutes. So, Aman, if you're comfortable doing that, that would be great. And the chat is recorded and the recording will be available to you post the session. Slides and resources, everything will be sent out to you after the session. So if you're not able to attend the full thing, please don't worry. And like, we'll keep you posted. And if you have any other questions, feel free to email me, Slack me. Like, we are all available. We also have a Discord channel. So yeah, I think we are good to go. Yeah, I think I've addressed. So yeah, your questions are being monitored. So feel free to ask away. I've just answered a question by Dwarkrama. So yes, can you go to the next slide?
Yes, yeah.
Yes. So, Aman, I'll give it away to you now. And thank you so much, everyone, for joining. Keep an eye out at the chat button. And to make the best use of your time, we would recommend that you follow the session hands-on because this is a interactive session. And make sure to check out Single Store because we're giving away $600 worth of free credits. Okay. Thank you.
All right, folks, we'll get started here. So I wanted to cover a couple of slides talking about the background behind what is single store and why we need single store. So let's talk about the what first, and then we can talk about the why and how. So the idea behind single store is fairly simple. We've got a whole bunch of AI workloads that we've been deploying in the industry. There's so many of these use cases that are now AI powered. But the challenge behind all of these use cases is to figure out how to funnel data to these models, right? Whether it comes to model training, fine tuning, evaluation, or even inference, right? Everything is powered by a significant data pipeline, which is centered around the model. And you can't have a deployment at the end of the day, whether it's any of these different workflows that I just talked about. All of them require a data pipeline around the model to be stitched together that interacts with the model and then carries out the desired function, right? So Single Store is, one such, database offering, and there's a whole bunch of other offerings from Single Store, not just Single Store DB, which is the primary database offering, but there's Helios and a bunch of different offerings that let you, connect with models pretty easily, have, database structured in relational form, even vector form, and be able to funnel data to your models very easily and seamlessly, as we'll see in the webinar where I've put together a problem statement where you'll see how data can be stored as a model's being, RL fine-tuned. That's going to be the topic for today. But the idea all loops back, to one simple thing, right? A one-stop data platform solution to build AI apps as well as analytics at scale. That's Single Store. Now, yeah, like I mentioned, there's a couple of different key aspects, right? That you're gonna power AI apps, but do that at massive scale, right? At billion scale is how we like to call it. And even if it's things like analytics or search, all of that can be powered pretty well with single store. and all of that at your SLA requirements, right? So that's another key aspect. Not only just powering these solutions, doing it at scale with your SLAs in mind. Now, who is single store, right? So this is yet another view of how single store has structured their growth over time, starting from 2011 when it was founded as MemSQL back in the day, and then currently to an indexed vector search with a lot of different milestones in between, right? So I'll spare you the details in terms of the milestones, but I do want to highlight a couple of key ones. MemSQL is where it started, and over time, around 2017 is when Single Store introduced vector search along with full text, right? So, and the key here is a hybrid system that can look at not just full text matches but also vector matches, right? And vector matches are essentially what are powering whole bunch of semantic matching AI-based workloads right now, where you generate embeddings or vectors out of input queries, and then you match them against a database. And the database powering a lot of this, keyword and vector search slash matching. Single store is one such offering that lets you do both, like I said, at scale within your SLAs. And later on, after beyond that point, around 2020, it got rebranded as Single Store and has, constantly been reinventing itself with a bunch of new features being added every now and then. You'll see some customers and ARR numbers on the slide. So at this point, Single Store serves over 400 customers. We're actually way beyond that. I think last I checked, beyond this number, and in terms of ARR, over 100 million in ARR. Now, this slide basically gives a quick overview of how a single store works under the hood, where you got your data pipeline that I was talking about earlier, and then you've got a bunch of different layers: the memory layer, the persistence cache layer, and as well as the object storage that powers all of these different key aspects, on top of it, right? So, and all of these basically essentially allow you to carry out, queries, and queries obviously undergo query aggregation as well, just like with any database. And these queries then ultimately serve individual users. Here, the teams put together a bunch of different links going over single store resources, so you can take a look if you're interested in the developer hub and documentation. For example, there's a whole bunch of different code snippets and examples in terms of how you can leverage single store for various different use cases, and a whole bunch of links to socials after as well on this slide. With that, we'll get started with the agenda for today, which is agentic reinforcement learning. And what we're going to cover today is we're going to talk about the theory behind, how reinforcement learning is powering LLM alignment and agents. And I've been involved in the industry at various different companies over time, putting together, more recently, putting together an agenda for reinforcement learning as it applies to building better LLMs. So we'll talk about why that is absolutely necessary, why we need RL. We'll also then touch upon the core RL algorithms that we've got today, PPO, DPO, and GRPO. And a lot of this is mathematically intensive, but I'll cover these at a top level. I also have a whole bunch of primers that I've written up, so I'll be sharing those as well at towards the end of the presentation today. So you'll see that in the further reading section at the end. But these algorithms will be covered just so you guys have a foundation for what's to come, which is the reward design. That's going to be the next agenda topic, and wherein we'll cover three different types of rewards: rule-based rewards, preference rewards, as well as generative rewards. And then we'll finally apply RL for tool calling to, we'll look at the DeepSeek R1 framework, which is a framework that was proposed in March of 2025, last year, which basically talks about how we can incorporate RL with rule-based rewards and teach a model without any human annotations, right? So if you want your model to, um, learn a new capability, for example, carrying out reasoning, or in this case, for the sake of this webinar, carrying out tool calling. How do you do that with a reward model that could be rule-based, that could be preference-based, or generative? So we'll talk about all of those three components. We'll particularly talk about rule-based rewards as well. And then finally, we'll talk about how you can use SingleStoreDB to carry out agentic tool calling, and how do you store RL prompts and preference data within SingleStoreDB as you carry out, in this case, RL fine tuning on your base model. So we'll touch upon that as well. I have a code, a notebook as well with code where I'll share key steps trying to link SingleStoreDB, to a model as you're carrying out RL fine tuning. So we'll touch upon that as well as part of the demo towards the end. And then lastly, like I said earlier, I will be covering some key primers that I've written up in, RL and agentic RL, reference optimization, and LLM as a judge, all of these four topics. And we'll also have a list of key papers for you guys to dig into if you're interested in the technical content, surrounding this topic. All right. With that as the agenda, let's get started with the motivation. So why do we need RL for LLMs? And like I mentioned earlier, in the industry, we're seeing, an uptick in reinforcement learning being applied to LLMs, and that is for good reason. And this slide touches upon why that is the case. So earlier we've seen, models being trained with next token prediction. That's, still the case for pre-training. That's still the case for supervised fine tuning. Now, when you do pre-training, in particular, you're training with next token prediction, categorical cross entropy loss on the web corpora that's available, right? So we've got data sets, C4, for example, common clean common crawl is an example where we've got the web synthesized in data set form, and then we have the LLMs predict next tokens. So that's been traditionally seen, in the field. We've done that for pre-training all of this while. And then we've had an SFT stage, which is the supervised fine-tuning stage. And this particularly teaches the model to imitate expert demonstrations, right? And what you've got here are a bunch of question and answer examples, aka prompt and response examples. And SFT teaches the base model that's pre-trained already to be able to answer questions, right? So that's the SFT stage. But the challenge with just continuing with SFT, which is what the field was doing up until early last year to the year before, was to utilize SFT, continue scaling SFT. And there are a couple of challenges with that, which is where RL has stepped in now, and which is that SFT optimizes for imitation. It teaches the model to, come up with the most likely next token. It does not teach the model, decision trade-offs, what it should consider, various different options it should weigh against. It has no notion of cost or, any form of long horizon reasoning, right? So this is a big challenge, and if you've got an LLM that you want to, adapt to, a use case such as tool calling, where you want the model to interact with the database, like single store in this case, as we'll see in the demo, your model must decide when and how and which tool to call. And all of those three key aspects of when, how, and which are essential to be taught to the model for it to gain a capability in terms of tool calling, right? So this is where RL comes in. And the objective behind any RL algorithm out there is to maximize the expected cumulative reward, right? So over time, if you're gathering rewards and you shape a reward function that assesses the success of the model calling tools, and if you're able to scale up this reward, the model is learning to carry out a particular task better, right? And the task is essentially defined by the reward function. So that is the entire RL paradigm, and we'll talk more about the reward function. We've got a dedicated slide about how you structure a reward function, and which is essentially how you teach a model a new trick, right? A new capability, in this case, tool calling for the purpose of this presentation. But that's the entire paradigm behind reinforcement learning. And as you'll see in terms of for each of the slide, by the way, I've tried to put in some pros and cons and when to use. So you'll see those bullets at the end. And for RL in particular, you'll see that RL optimizes real outcomes instead of just pure demonstrations, which is what SFT does. And cons, obviously, you need to, like I said, reward design is the heart, at the heart of any RL process. So, it requires careful reward design and does require running the model multiple times during inference, as we'll see it in the demo, which is essentially called a rollout, and does require compute. So that is the key aspect. But the biggest advantage here is that you don't need human annotations, as we did with supervised fine tuning. And when to use, like I mentioned earlier, for reasoning, for tool use, RL is pretty essential, and tool use is the topic for today. So we'll delve into that. But you can utilize RL for all sorts of different use cases where you can have the model explore different possible options and then reward it for a particular trajectory or a particular option that seems likely and seems plausible given the current context. All right, with that, we'll move on to policy gradient foundations. And by the way, these are a lot of different topics that you need some background in before we get into, the crux of today, which is utilizing single store to carry out RL fine tuning. But let's get started with, some background at top level. And if you need more details, I have resources linked towards the later portion of our presentation today in terms of primers and papers. Um, but to give you a quick background of policy gradient algorithms are one particular type of RL algorithms, and the idea is pretty simple, where you basically have a policy which is, the actual main model, the LLM, and the policy basically maps prompts to tokens, right? Because if you take a look at the model, what you're essentially doing is feeding in a prompt, and it comes up with an output, right? Which are the output tokens. So that mapping is essentially what is defined by a policy, which is, like I said, essentially the main LLM model. And what we do is in a policy gradient algorithm, we maximize the expected rewards using the gradients of the policy distribution, right? We're using the gradients of the main model. And this basically this powers the update tool that is used in most of the modern RL algorithms. This is what updates the model, or RL fine tunes the model in technical terms, as we're feeding it data, right? By data, I mean input prompts. So what we do here as part of RL is that we've got a couple of different components. And advantage estimates are one big component, as you'll see in the equation I have here. The A here towards the right hand side of the equation is the advantage, and this advantage basically measures how good a particular next token is relative to all of the other tokens in the vocabulary of the model, right? And as long as we're seeing an advantage, a positive advantage for the right token, we're headed in the right direction, right? So that's the entire idea behind RL fine tuning, to maximize the probability of, what the next token would be, and be able to do that given the current context, right? So the context is all of the input prompt given so far, as well as all of the tokens that it has generated so far, right? So if you put together the input as well as all of the tokens amounts generated, given all of that as context, what is the next likely token, right? So that is the what we're trying to optimize with the policy gradient here. Um, and the pros here is that you're trying to drive the model behavior, steer the model behavior towards higher reward trajectories. Because the advantage does, as you're calculating the advantage, you are looking at the reward. It is part of the advantage calculation, the reward that the model is receiving as it generates one token at a time, and thereby you're steering the model in a direction that maximizes these rewards, right? That maximizes the probability of it coming up with an output that suits the input better based on the criteria that that you've put in together as part of the reward design process. And cons, the challenge here is that this could lead to high variance without a baseline, and we'll see in the later slides how we can create a baseline to optimize this further. Um, and the use case here is essentially to train LLM models where the actions are sequences such as the text tokens, right? Which is the entire use case behind an LLM model to be able to output text, right? Given a particular sequence of input. So this is where policy gradient algorithm comes in, and all of the RL work that's been happening in the field, just to give you guys some context, are forms of policy gradient algorithms being applied to LLMs. There are a couple of other types of RL algorithms too, deep Q networks, for example, and a whole bunch of other options that are available. But policy gradient algorithms are key for the success of LLMs and all of the key advancements that we're seeing in LLMs today. All right, with that, we'll move on to the first type of policy optimization algorithm, which is called PPO, and it is one of the most widely used policy optimization algorithms. And again, this is one a particular type of a policy gradient algorithm that we saw on the last slide, and there's a bunch of different types that have come up. And there's actually hundreds of them that have come up, but we'll cover three of them in at the top level today in some detail today. So you guys have some background before we get into code. And The idea behind PPO is that we want to be able to, tackle the biggest challenge with RL, which is stability. And the way PPO improves training stability is that it limits how much the policy can change per update, right? And the way it does that is by using a clipped surrogate loss, which is what you'll see in the equation here. And again, don't need to worry about the particular equation. I just wanted to include it here for reference, but I intentionally did not cover all of the different terms within the equation, for example, on the slide, because a lot of these details, you can acquire offline. And like I said, I have shared primers and other resources later on for next level detail. But I did want to make sure that you guys get a top level understanding of why we need these algorithms, right? So coming back to PPO and the particular loss function that it has here, what it does is that it ensures that every step of RL fine tuning, the model does not, go beyond a certain, area, as far as its updates are concerned, right? So this is the entire idea behind constraining the updates, so the model doesn't undergo instability where it starts outputting, junk, and so that is the entire idea behind PPO. And the intuition here, like I said earlier, is to improve responses that have a higher advantage, that have a higher reward, essentially, while you're clipping updates to prevent, significant policy changes that can steer the model away from, generating coherent and meaningful text, right? So that is how PPO is set up, and PPO is the main algorithm that powered the biggest advancement that we saw in ChatGPT a couple of years ago, which led to a lot of success, with ChatGPT a couple of years ago back in 2022. So PPO was key to that success, and PPO is inherent to a pipeline called RLHF, reinforcement learning with human feedback. And you'll see that on the right hand side here on the slide in the diagram, where you've got three steps with RLHF. And the first step is obviously to collect demonstration data, from humans, where we figure out pairs of data outputs that are preferred versus dispreferred, also called chosen versus rejected for a given prompt. And we train a policy around that, right? And that's actually step two after you've trained a base model, right? You pre-train a base model. So once you've got a base model, you collect some of this comparison data, train a reward model around it. And then lastly, you use both of these models put together, the base model as well as the new model that you trained, the reward model, and you optimize a policy, the main model, which is the policy, against the reward model using reinforcement learning. So these are the three steps that we see typically in any RLHF pipeline. And that was PPO at a top level. And what happened a couple of years earlier, back in 2023, was this proposal called as DPO, and I've linked the paper here, which basically obviates the need for any reinforcement learning altogether, right? So DPO basically says that you can, optimize your main LLM model without training a separate reward model, right? And if you remember from the last slide here with PPO step number two, we were training a reward model in the diagram in between, right? Now, TPO basically says that your LLM itself can serve as a reward model. And we saw a lot of success with DPO in the field. A lot of different research, papers and industrial implementations that utilize DPO. But over time, we realized that we were losing performance. You're using DPO versus PPO, and there were a lot of studies that were papers that came out comparing DPO versus PPO on the same task. And we saw that there was a performance gap, which is why the field went back to reinforcement learning. So I'll talk about, a successor to DPO, which actually builds on PPO and still utilizes reinforcement learning, which is way more newer and has a lot of benefits compared to PPO and DPO. So that's going to be the next slide. But coming back to DPO here, the idea is that you can have a similar set of prompt and preferred and dispreferred responses, triples, which are corrected from annotators. And all of this data again has to live somewhere, right? So this is where single store also comes in, where you can house all of your data, within in this case, a relational database, and then funnel that through as you're training a reward model, right? Or in case of DPO, you're not precisely training a separate reward model, but then the data has to still live somewhere so you can carry out, fine tuning with the loss that's mentioned here, which is the DPO loss, and thereby optimizing your main model, right? So that's typically the flow that we see in the industry, data being housed in a backend. Backend typically needs to support full text plus vector searches. It could even support multimodal data, which is another area where single store really shines. So there's a whole bunch of different aspects that we typically look at as we figure out what databases to choose. Now, with DPO, the idea was the intuition here was to increase the likelihood of preferred responses relative to the dispreferred ones, while at the same time making sure that you stay close to the original model as much as possible. So you'll see simpler training as one of the biggest advantages of PPO or DPO in this case, because there is no reinforcement learning, right? So things get pretty optimized. All you're doing is just being able to you're fine tuning the model with that equation on the slide. Um, but the challenge with that is that because you're getting rid of reinforcement learning, like I said earlier, we did see a dip in performance, with dedicated papers that came out later comparing PPO versus DPO on a particular preference data set. And we saw that PPO performed way better than DPO just because of the RL aspect and because we were limiting exploration. Um, this is an offline alignment strategy because you do not need to carry out RL loop live as you're, training a model. But the offline alignment is if that's what you need, you have a static data set of preferences that you put together. And you can carry out offline alignment pretty easily with TPU. Now, coming to the last policy optimization algorithm for today, which is GRPO. Like I mentioned in the last slide, this is the algorithm that was proposed recently as part of DeepSeek R1. DeepSeek R1 actually utilized it. DeepSeek Math was the paper that actually proposed it back in 2024. And this base GRPO builds upon PPO. So it still utilizes reinforcement learning, but it gets rid of one of the key negatives of PPO, which is to train a separate value model or a critic. So if you look at the GRPO equation, the advantage, components, the A components that you see there, instead of having a model, come up with a particular, a value estimate, right? Which is what we saw with PPO. All you have to do is just carry out normalization. So you'll see the equation for A down below, which utilizes the mean and the standard deviation, and thereby obviating the need for a separate model that was coming up with the value baseline as you would normalize your rewards. So basically, in a single line, GRPO is it's an efficient alternative to PPO. And otherwise, it's very similar to PPO beyond the particular the idea of obviating the need for the value model or the critic, as it's commonly called. So this is a quick optimization that we've had, and DeepSeek actually utilized GRPO to teach reasoning to a base model. So that's they utilize GRPO to with rule-based reward, as we'll see in the later slides, to teach a model to reason better. And this was one of the biggest innovations in all of generative AI and reinforcement learning from March of last year. So GRPO has had quite a big footprint in the field and has led to a lot of good impact. And if you look at the intuition here, it is to compare the sample responses. So you get take a model and make it generate a whole bunch of different responses. Um, and you're increasing the probability of output that score above the average of the group, right? So if you've got a whole bunch of these different responses, you can come up with the average of all of those different responses, aka rollouts is what they're commonly called. And then what you do is we just increase the probability of outputs that are beyond the average of the rollout. So that's the entire intuition. Now the pro here is that because you're not training a separate value model, you don't need to house that model in memory. You don't need the compute. So memory and compute usage is something that's a big benefit in terms of lower memory and compute usage. Cons, it does require multiple samples to be generated per prompt to generate these group relative advantages. The AI equation that we're looking at on the slide. Um, Now, if where do you what kind of use case do you use GRPO for? If you're looking to train reward model reasoning models where you can generate multiple solutions, you have the compute to do so, and you can compare them. You can use GRPO to introduce reasoning in a model. You can use GRPO to do any kind of rule-based checking, as we'll see later on. Say, for example, you want to teach a model to carry out computer use or do web browsing. A lot of those different applications become way more easier with GRPO, especially with rule-based rewards. Now, the next aspect is reward design for agentic RL, and the idea here is to, cover how you can incentivize any of these algorithms to start steering the model in the right direction, right? And all of that is controlled, with this key aspect, which is designing a reward function. Now, rewards, the idea is that if a model generates an output to a particular prompt, how do you grade the the particular output along various different criteria to come up with a reward that can be used as part of the whole RL fine-tuning process? This is the entire idea about reward design in one line. And whether it's if it's in reasoning, for example, there could be intermediate reasoning steps, there could be tool usage. All of that has to be graded or verified for us to understand if the model did a good job or not. And this is what reward design is centered around. And we'll talk about three different aspects, in terms of how we do this. There's rule-based rewards that I mentioned earlier for on the GRPO slide. There are also preference rewards. Preference rewards are similar to what PPO did, where they actually trained a reward model with preferred and preferred pairs of outputs per prompt to be able to understand human preference. And lastly, we've got another type of rewards, which are generative rewards, essentially LLMs that are other LLMs, frontier LLMs, for example, that are used to grade the output of the model that you're looking to RL fine tune, and then assign a reward back based on various different criteria that you care about in that particular output. It could be structure of the output, it could be the accuracy of the output, the amount of hallucination that exists, for example. All of that can be graded by a frontier model serving as a judge, and then assigning a reward back in the RL pipeline. So these are the three types of different rewards, and each of these offers different trade-offs in terms of scalability, cost, and how reliable it is. Now, the pros here obviously are, figuring out how we can optimize a particular base model, a complex agent across multiple different steps. That's what we use reward design for as part of agentic RL. And in terms of cons, if you design a reward function poorly, you're incentivizing the model to learn something but do it in a manner that does not actually teach it how to carry out a particular task, but just learns how to maximize reward. So that's called reward hacking. But otherwise, we've used reward design in terms of use cases for reasoning, tool planning, tool use, and planning. And tool use is a particular area that we'll talk about, in the coming slides. But as long as you can design a reward that assesses the right criteria within the output, you're able to teach a model how to carry out a particular task pretty well. So this slide I've put together here covers the three key types of rewards in a lot more detail. So you'll see that rule-based rewards, preference rewards, as well as generative rewards are the three key types as we touched upon in the prior slide. And with rule-based rewards, you're essentially doing a code-based evaluation where you're looking for a particular, criteria in the output to be satisfied. It could be an exact match where you're looking for a certain output. In particular, it could be that the model generated a tool call and you want to make sure that the tool runs. So you run the tool in a separate sandbox environment as it generates the function call. Take that call, run it, and then understand if it ran it successfully or not. So with an error code of 0, for example, that would be successful tool execution. So that's yet another type of rule-based reward. Now, if your LLM generated a JSON, you can check if it's valid or not, if there were syntax errors. So JSON validity can also be checked in terms of rule-based reward. And with preference rewards, where you cannot apply rule-based reward is typically where we utilize preference reward, where we have humans to compare two sets of outputs and figure out which better answers the particular prompt or the input query. So that's a preference reward, much like what we saw in PPO where we trained a reward model, right? So that is a preference reward where where we're coming up with a model. We're teaching a model to understand human preference. So that's human preference rewards. We've got generative rewards, like I mentioned earlier, where we just use an LLM as a judge. We give it a whole bunch of different criteria to judge a particular model response by, and it comes up with a final score against that criteria. So these are the three key, different types of rewards, and all three serve different kinds of use cases. The pro here is that they offer flexibility, where you can choose which one you like based on your particular use case and what kind of verification or assessment you can do as you're coming up with the reward. You can even mix and match a couple of different components. We see that very commonly in the field. And in terms of cons, if you're using, say, generative rewards, you could see some bias because LLMs as judge has a lot of different forms of bias. So the success of your RL system will totally depend on how good of a reward signal you set up, which means if you use generative rewards, you want to make sure that they're free from bias. But in terms of the use case, like I said, you can mix and match and verify different aspects of an output along various different, principles, choosing from one of the three here, and come up with a reward function that can have a lot of these different components assessing different parts of the main model, the LLM model's output. Now, DeepSeek R1, this is a quick overview to how DeepSeek R1 utilized RL to, teach a model to reason. And the reason why I wanted to touch upon this is because the demo that we have, the code that we have today is centered around GRPO, which is what DeepSeek R1 uses. So I'll cover this, quickly to make sure that you guys have some background before we get into how we can use GRPO, and funnel data through SingleStoreDB and utilize GRPO with a base model. We'll be using Quen in our demo, and that will essentially teach a model to carry out, natural language to, tool calling for SQL queries with SingleStoreDB. So that's the goal here. That's the topic that we're working towards. But to get there, it's important to understand what DeepSeek R1 proposed, and I've got the block diagram on the right with various different stages. But the idea is simple. What we typically, if you look at the training stages here, DeepSeek R1 basically starts off with a cold start. supervised fine-tuning stage where you've got a small curated data set that it teaches the model what kind of reasoning format to have in its output, and for both reasoning as well as non-reasoning data, it shows it enough samples in terms of how it should respond in that particular output format. So that is the early stage cold start SFT, and then we've got RL with rule-based rewards as well as preference rewards. So those are the two key aspects where for with rule-based rewards, you can easily verify tasks such as mathematics, coding, logical reasoning, all these reasoning tasks that can be easily verified. And keep in mind, the paper actually utilized multiple choice questions for various different aspects. For example, STEM, questions as well, or STEM prompts as well, where the model had to choose from one of the 4 or 5 options available, which made it a easily verifiable task, right? So that's where rule-based rewards came in to teach the model how to reason. Now, RL with preference rewards is yet another different option, which uh, is how the model learned how to carry out non-reasoning tasks better. So the paper, even though they fixated on reasoning, they actually utilized both rule-based rewards for reasoning as well as preference reward for non-reasoning tasks as well, such as improving writing quality or making sure the model is helpful and offered good conversational responses. So both aspects existed for both, for reasoning as well as non-reasoning tasks. And in terms of the key innovation that this paper proposed was essentially rule-based rewards, as we'll see in the demo as well, where if you prompt a model and have it generate an output, and if that output is very easily verifiable with a basic piece of code, say Python code, it can easily scale, RL without needing any kind of human annotation. So that's the entire thesis behind what DeepSeek R1 proposed. And in terms of use cases, when you want to teach a model reasoning for math, coding, STEM, logical problems, rule-based rewards serve, the model pretty well. So this is what we've been seeing in the field where, easier the verifiability of a particular task, the more easier it is to teach a model that particular task because it's easy for you to gauge how good it is at doing it as it's being RL fine-tuned. Now, we are now getting one step closer to the final demo, which is tool calling. So if you look at the examples on the right, I have a tool call here, which is a structured JSON output. This is the output from a LLM, where it's making a tool call to query SingleStore DB, right? And for that matter, you can have it query any kind of database, but this is how we've structured it, where it can call a particular function with a particular query as an argument, and it comes up with an expected result. Now that was the first, tool call output on the top right, but you'll see the tool call execution output as well, where once you've come up with the tool call, you can utilize that tool call, to be run in a sandbox environment outside of the LLM, obviously, and then come up with an answer, which will serve as the final answer that gets further inserted back into the prompt of the model for it to carry out next steps. So to generate this particular tool call on the top, right, is essentially what we're going to be working towards in the demo, where a model can come up with, queries into a single store database with natural language as the input. And these queries are obviously SQL queries, as you can see in the example. So as part of this, what we're going to do is we're going to teach a model, a couple of different things, right? We're going to teach it when to call a tool, because not all queries might need tool calling, right? So that particular aspect needs to be taught as well. You need to teach which tool to call and how to call the tool. So we see all of the 3 different examples or 3 different criteria and aspects as we RL fine-tune the model. Now, where does SingleStoreDB come in here, right? So I've got a diagram here on the right that basically illustrates that you've got your RL prompts, which are the input prompts. This can include not just the input prompts, but also the tool descriptions, also the schema of the database that it's querying. So all of that input can reside in single stored DB. Along with that, you've got preference data, you've got good trajectories as well as bad trajectories that can also reside, in a database, in a particular table, for example, within the same database. And that put together can power agentic training, where you're having a model that is absorbing, taking in the input, and then understanding, what that it needs to prefer good trajectories, good outputs versus the bad outputs as part of the RL fine-tuning stage, and that's how you carry out RL optimization. So all of that data can be housed in single stored DB in various different tables within the same database. Now, I've got, like I mentioned earlier, I know this was a lot of dense material, but the devil is in the details with a whole lot of these different concepts, and I've put together a whole bunch of different primers that cover a lot of this in detail. So if you're interested in learning more about the equation that I had on the slide and how a lot of these algorithms work under the hood, I have a lot of that covered in my reinforcement learning primer. I've got an agentic RL primer as well as policy optimization and LLM as a judge primer. So take a look if that's of interest. But I've linked all of them here in the slide, and we'll also be sharing the slides so you'll get access to these resources later as well. Also put together a list of papers, key papers that have shaped the field. So we've got various different algorithms, RL algorithms. We've got RLHF as well. We also have papers around agentic RL that have been, which is a very hot area of research right now. So I've put together a bunch of different papers there as well. So in case you'd like to dig deeper into technical content, some further pointers for you guys to look at. All right, with that, we'll move over to the demo. I believe we've got about 5 minutes or so before we get into Q&A. So I wanted to make sure I leave 10 minutes at the end, like we discussed earlier for Q&A. But if you've got any other questions, feel free to reach out. But just wanted to make sure that there is enough of a background before we get into the demo. All right, and then with that, let's see. All right, so I've got a single stored notebook here put together that basically uh, does agentic tool calling with GRPO, which we just discussed. And the idea behind this particular notebook is that we're going to be talking about a whole bunch of different areas. We're going to be talking about how we can, sample a particular prompt. If you've got a whole bunch of different inputs or prompts stored within a database like single store, step one is to sample a particular prompt from that particular database to be able to run it through the model. So that's called the prompt sampling step. We're going to then talk about taking an open source model. In this case, we've taken Qwen 2, which generates multiple different candidate tool calls. And all of these tool calls are emitted as structured JSON. That's how all of the models typically do it. It's in the form of structured outputs, typically JSON. And then we'll talk about tool execution as well, where we take that particular tool and then we execute a query against a single store database. And then as part of that, we're also going to be generating rewards. And these rewards are then funneled into the advantage computation that GRPO calculates, where it normalizes rewards within a particular sample group using group normalization, which is the core essence of GRPO. And all of these different interactions through the model, right? We call them trajectories in RL terminology. All of them, the prompt, the model output, SQL query, the reward, the advantage, and also the step number. All of that will be stored in single store as we're carrying out the entire flow. And not just that, but also analytics and monitoring. That's yet another area that is very important as we are carrying out these steps. So if you've got any reward trends and policy behavior and any success rates or metrics that we need to monitor, all of that can be packaged in the backend as well in a single store database. So now in terms of the key aspects here that power this particular flow, right from storing RL trajectories to analytics and being able to support fast inserts and queries. All of that is, are areas where single store is pretty good at. So, that is one key. These are some key areas where we'll be doing database queries and storing all of this intermediate information as we carry out the RL fine-tuning loop. And this is the particular architectural flow, as you'll see on the slide, where we've got a prompt coming in, we've got that being fed into the LLM model, which is the policy. Qwen 2.5 is what we're using. Now, this policy, this model is going to generate a tool call, which is essentially going to be a SQL call that will feed into that will query a single store database. Now, the out whether the query was formed, per our expectations or not, whether it was malformed or it ran successfully, will determine the reward. The reward gets funneled into the advantage, like I mentioned earlier, and all of this data then gets stored into single store, including the analytics and monitoring. All right. So with that, let's start getting into code. So here in the first step, you're just installing the required dependencies. I've actually run the code, so we don't have to spend time loading all of these things, which do take a little bit of time, but you'll see the output right here for each cell. For cell 2, we're just importing the libraries, loading the open source model. Qwen 2.5 is what we've used here, so you'll see that being loaded. And by the way, the notebook is going to be made available later today as well. Yukti will make it available. So feel free to dive in if you'd like to learn more and want to run this against your particular instance. We have an instance that is set up here with a database connection. And we're just setting up the tables here within the database by running these SQL queries at this point, just trying to structure all of the different tables that will house all of these training metrics and analytics as we carry out RL fine-tuning later on in the code. Now, at this stage, we are just setting up the particular database tool that and coming up with the query single store function, which is what the LLM will generate as a call later on. So just writing a wrapper around that so the LLM can utilize a wrapper function as it does a call. Now, this is the prompt to the main model that gets fed in, right? So you are an AI agent that can answer questions by calling a database tool. And, we are basically asking it to respond in a JSON format. So this is an example that we're providing it. This is the function call that I spoke about earlier, query single store. And we're asking it to just return a JSON without any explanation. So this is how we're structuring the prompt. Now, the next cell basically generates tool calls from the LLM, where we're basically having the input be tokenized and then having the model generate the output. And we basically have it do it for four different rollouts. So the group size is 4. You can set it to whatever number you like, but this is what controls the success of the GRPO algorithm. Bigger the group size, more the outputs that will be sampled, which means more the compute that'll be used, but better the RL fine-tuning success that you'll see. Now, this is where we actually carry out the tool call. So you'll see in the output that it says functions ready, and same way here, this is where we generate or compute the rewards. So this is where we are checking if the SQL ran successfully or not, the SQL that was generated by the model. And then finally, what we do is we've got a toy data set here with a couple of different examples in natural language. So you'll see how many trajectories are stored in the training data and a correct SQL for that as well, versus a different prompt such as what is the average reward in the training data versus show the learning curve of the agent, and SQL queries for each of these different prompts. So we've got, this is our data set that is essentially stored in a single store DB instance. But as we carry, this is the main GRPO training loop. So as we carry out GRPO based RL fine tuning, we're going to basically generate multiple different tool calls like we saw earlier with a group size that's specified here. And for each of these tool calls, we're going to execute them. And based on whether they executed or not, we're going to come up with a reward, and which is right here. Reward is compute reward. And then we're going to average it out and generate the advantage, which is what feeds into the RL fine tuning loop. So the demonstration here is to make sure that we're able to utilize some data to teach a model to carry out natural language to SQL queries, which is a very common use case in the industry. And essentially, that if you look at the outputs here, you will see that for each of the input queries, it's generating a particular output. And so you'll see select count star from group samples. You've got another output here, select average reward from group samples. So the model is able to generate SQL essentially, and it carries this out for various different steps. We've only done the fine-tuning loop for about three or so steps here, but it's a good idea typically to run it for a whole bunch of different steps as well, as you see the reward going up and the loss going down. So that's typically the strategy we see. And then once we've got all of that generated, what we typically do is, like I mentioned earlier, with any kind of production flow, we want to make sure that when a model is trained, we also have enough analytics around it to understand what kind of course it took during its training trajectory, right? So we've got total trajectories here and average reward here, and you'll see the outputs here. So that's what we typically look at as we're RL fine-tuning a model. But yeah, with that, I think we're only 4 minutes to the end of today's presentation. So I'd like to make sure we have some time for questions. But I'll stop sharing my screen and we'll share the notebook as well so you guys can take a look at later on. But yeah, here for any questions.
Thank you so much, Aman. This was such a rich session, and it's one of the best sessions that we have done in a long time. So thanks so much for preparing so much of content for us. So we have a lot of questions for you. So for everyone that has just joined us, we are officially live with the Q&A session. And if you have any questions, feedback, comments, please add them here in the Q&A box, and we'll take them up, try to take them up live because we have a bit less time remaining. So, Aman, can you access the Q&A button, or would
Okay.
you like me to? Okay, okay. If
Yeah,
you
yeah.
want me to read it out for you, that's also okay, though.
No worries. I can see the questions here. Let me try to go over them quickly. I'm just trying to figure out which questions. I think we can cover a bunch of them quickly, so no worries. I see a question from Ashish Asthana. Could you share the embedding size for this particular use case? BM25 supported. BM25 is supported. It is a traditional lexical, search method, very commonly supported. There is also a hybrid full text search plus vector search mechanism that's supported with all kinds of, leading offerings. Single store has that, feature as well. All right, Deepanshu has a question. Earlier, there used to be a way through which log probabilities would be possible to tweak as the model parameters were converted. Why is that? It's a great question. You can access log probabilities with open source slash open weights models. Close weight model do not expose that now. But with the API, I do believe log prob is equal to 2. If you set that for, say, the GPT API, you should be able to access it. Last I checked, but the model providers are more and more trying to hide this as an option because at the end of the day, you can use that as training data. That is the primary reason why this is going to go away if it hasn't gone away already. How do we untrain any data sets from an SLM? I'd like to let go some of the data that are not serving my purpose and train SLM with specific data sets. How do you tackle this? Very good question. There is a whole field of research. It's called machine learning. And the idea is fair and simple. What we do here is gradient-based learning as we train a model. With unlearning, we figure out the particular neurons or units within the model that impact a particular output, which is a fact, say, that you want to forget, with the model. And we send gradients to those particular neurons in a targeted manner that essentially have it lose track of these facts. So machine learning is a whole research area, and I'd recommend looking into papers there. I have a couple of papers coming up in that area as well. But again, many different ways to do this. But everything boils down to the fact that we're gonna set gradients to neurons and impact what they have stored within their weights. Shaji mentions policy gradient algorithm. How can you reliably interpret whether a model chose one action over the other as internal state remains hidden? That's a good question. Observability is again a whole field. So that's what your question's hinting at. It is very difficult to monitor internal state. I do want to be transparent about that. That's just how these models are. But you can get a sense of that in aggregate where you look at these reward and loss metrics and understand if the model is able to head in the right direction based on the reward model. Also, if you have noisy feedback, how would you reduce training time if you end up spending a lot of time filtering signal out of the noise? We have data quality metrics. That's what we typically use, in any kind of deployment. All of the data quality essentially needs to be gauged before you fine tune or do anything with the model. Dipanshu has questions around browser agents. Yes, the rewards for those are challenging, especially because they are long horizon tasks. So browsing agents will take a little while before they are successful, but I mean they're pretty reasonably good already. So give it a little more time and you'll see a lot more success with browsing tools. Ashish had another question. Good technique to create data for fine tuning NL to SQL. Yes, I have a paper on that from NeurIPS. Take a look at that on my Google Scholar for NL to SQL. That should give you some good idea about setting up an agentic system around it. And that you can use that to generate data. Dipanshu, what are some research questions we could pursue given the state of the field? Um, you can write to me over email. I can suggest some research questions. This is pretty open-ended, but I can give you a lot of different pointers. Alex, how do you see this going forward? Enterprise setting, AI platform offers this service and ability to tune parameters. This would be a question for the single store team. Now, in terms of the ability to do hyperparameter tuning, there are services. Bayesian parameter optimization is what most of these services typically use. With you can do grid search and random search. Um, I can't comment on the other offerings here from other companies, but I would say contact the team at SingleStore and they can give you a good idea of enterprise offerings. And last question is, what are things you're currently focused working on these days? What's making me awake? Um, yeah, there's a lot of different areas in the field, a lot of interesting problem statements. I'd say AI adoption for the enterprise is definitely a big thing, and single store is, a front leader in that space. So, a lot of different problem statements, in that enterprise bucket is what I'm currently busy with. And I really enjoy being in this space because just the kind of impact that you can create. So, yeah. All right. I think with that, we are done with the questions.
All right. So thank you so much for addressing all the questions. And thanks everyone for joining. Whoever that joined late, please don't worry. We'll be sharing everything over email. The recording will be with you soon in our follow-up email. And we have amazing sessions that are coming up in the future. So please stay tuned for that. We have an amazing session in April that is with Aman's colleague Vinija. So they have multiple research projects together. So that's definitely going to be a good session as well. So if you enjoyed today's session, please feel free to check out more sessions by us. Like that's going to happen next week, this week, and yeah, we are having more sessions next week, and then more the weeks coming forward. And yeah, I really enjoyed hosting, and Aman, I also learned so much today. Thank you so much for putting everything together, and I hope it brought value to everyone who attended. So yeah, all right, thank you so much, and I hope you all have a great rest